Today, we will be discussing dynamic rotor balance of the Velos V3 helicopter. My name is Alan Burtness. I will be your guide. Let's get started. In today's world, helicopter main rotor and tail rotors should be dynamically balanced or spin balanced with an analyzer kit to reduce the vibration levels of the rotor blade assemblies. To balance any dynamic component or assembly, there are four key pieces of information that need to be known for vibration mitigation. They are RPM, phase angle, vibration amplitude, and accelerometer orientation. Phase angle and vibration amplitude will be displayed on the ground station polar chart for analyzing. But first, let's talk about the components used to capture this information. Velos uses a balance system manufactured by Cooler Vibe, which allows in-flight vibration analysis. Included are the onboard sensors, which will be installed before the balancing flight. The circuit board analyzer carried onboard Velos used in this presentation is a beta unit used for proof of concept and extensive flight testing. The commercially available system will be greatly reduced in size. Also included are telemetry communications to a ground station analyzer. Balancing the rotor systems can provide substantial reductions in transmitted vibrational noise to the autopilot. These vibrations can confuse the autopilot sensors with its position in 3D space, causing a greater number of autopilot corrections and servo movement during flight, which can decrease flight path accuracy, service life of servos, and flight control linkages. Vibrations can also increase possible damage to the aircraft and its payload or blurred camera or video images. Dynamic imbalance can be caused by a mass imbalance or with physical weight differences with rotor blades or hub assembly. Rotor imbalance can also be caused by an aerodynamic imbalance because of a blade or blades being out of track with each other. Aerodynamic imbalance will be mitigated by ensuring all main rotor blades are matched in pitch using a digital pitch gauge to a reference 0-degree pitch setting. No other adjustments in individual blade pitch are necessary to achieve ultra-low vibration levels once physical mass imbalance has been corrected using hub weight. Balancing does not reduce the vibration level if the motors or aircraft is in poor mechanical condition. Defective, worn, or loose parts will make balancing impossible. Before dynamic balancing can be achieved on the main rotor, the blade holders and blades must be modified with the 2-bolt blade retention system. The single blade bolt retention method does not maintain consistent span-wise blade alignment, and because of this, ultra-low vibration levels are very difficult or impossible to achieve. The vibration level will increase or constantly change over time because of blade creep or span-wise misalignment of the blade in the blade holder. The 2-bolt blade retention system eliminates this completely. The onboard Cooler Vibe dynamic balancing system consists of a vibration sensor or accelerometer that is attached to the forward end of the payload rail that senses the amplitude of the airframe vibration in inches per second. The accelerometer senses all frequencies along its longitudinal axis, but we will only be interested in the frequency or RPM of the main rotor. 1,245 RPM and the tail rotor 7,000 RPM for the balancing process. Your operational RPM due to mission requirements may vary, but it is important for optimum dynamic balance to be achieved that the RPM being flown for the mission is the RPM being flown for the balancing flight. When balancing the tail rotor, the accelerometer and IR optic eye will be attached to the tail case and only used during ground balance procedures with the main rotor blades removed. Tail rotor balance will be discussed later in the presentation. To sense frequency or RPM, the balancing system uses an infrared or IR optic eye or tiny eye that senses the blade target or reflective tape attached to the bottom of a single main rotor blade. From now on, that blade will be referred to as the master blade. As the reflective tape passes over the optic sensor, it will trigger a count to begin in the circuit board analyzer and identifies that specific location of the blade to be at the 0-degree position for determining phase angle and to determine rotor RPM. The infrared optic eye is attached to the rear of the analyzer circuit board, which is mounted forward of the GPS antenna on the tail boom. The analyzer circuit board senses rotor RPM and master blade position reported by the infrared optic eye and vibration amplitude reported by the accelerometer, then calculates the phase angle of the maximum vibration impulse of the accelerometer in degrees and actual RPM of the rotor. The maximum vibration amplitude in inches per second, phase angle or location of the maximum vibration impulse in degrees and rotor RPM is then sent to the ground station computer by telemetry to be displayed on the polar chart for assessment of the vibration level. At this point, we have a basic understanding of RPM sensing with the IR optic eye or tiny eye, the phase angle of the vibration supplied by a collaboration between the IR optic eye and maximum impulse felt by the accelerometer and the vibration amplitude supplied by the accelerometer. So now that we know what the phase angle of the vibration is and its amplitude, how does the analyzer determine where the weight is to be installed on the main rotor balance disc to correct the imbalance? That is determined by the orientation of the accelerometer on the airframe. The orientation of the accelerometer mounted on the aircraft is the key component in determining where the balance weight will be correctly installed on the balance disc. The design logic of the accelerometer is that the cannon plug side will always point toward and determine the heavy side of the rotor disc, and the threaded side will always point toward and determine the light side of the rotor disc. Let's take a closer look at the polar chart used to calculate the vibration's phase angle and amplitude. The polar chart is made up of radial lines representing compass headings in degrees and 10 concentric circles representing the severity or amplitude of the vibration. The smaller center ring represents a vibration level of 0.1 inches per second, and the outer ring represents a vibration level of 1.0 inches per second. Remember, 0 degrees on the polar chart represents the location of the IR optic eye, which is mounted on the tail boom of Velos, so 180 degrees on the polar chart would represent the nose of the aircraft. For an example, let's say you hovered Velos out of ground effect to check main rotor dynamic balance, and looking at the ground station display, you see it plotted the vibration location or maximum impulse of the accelerometer at 240 degrees at an amplitude of 0.6 inches per second. This is an unacceptable vibration needing correction. The analyzer will give you instructions on how much weight in grams to add to the light side of the rotor disc. Do you remember the logic of the accelerometer? The analyzer is programmed to know the orientation of the accelerometer, and based on that information, it will tell you in degrees on the main rotor balance disc, which we will discuss in a moment, where to add the weight. In this photo, you can see the beta version of the main rotor balance disc mounted on the POR, to which we will add the balance weight. The production balance disc design will be located lower on the hub to allow the use of the POR for other devices needed for a mission. The 3D printed white cap was added to help smoothen the airflow over the disc in cruise flight. The aluminum rotor balance disc is 152 millimeters in diameter with holes drilled for balance weight every 15 degrees with the 0 or 360-degree hole being located at the center line of the number 1 or master blade, which has the reflective tape installed on the bottom of the blade for use by the IR optic eye. To my right, you will see the main rotor hub superimposed over the polar chart with blade position number 1, or the master blade at 0 degrees over the IR optic eye mounted on the tail boom. The accelerometer is positioned at the forward end of the payload rail, pointing forward toward the nose of the aircraft. The vibration in our example is plotted at 240 degrees at 0.6 inches per second. To find where the balance weight will be installed, we will position the master blade or blade number 1 over the reported phase angle position of 240 degrees. with the accelerometer orientation pointing forward toward the nose of the aircraft, identifying the light side of the rotor disc. We will always install the required balance weight at the most forward balance hole position, or in this case, the 300-degree balance hole, which is the most forward position on the disc. So you are saying to yourself, wait a minute. He just said the solution called for balance weight to be installed at the 300-degree location on the balance disc, but it appears the weight was installed at 180 degrees. Always remember the location of the balance disc holes begin at the center of the number 1 blade or master blade at 0 degrees and continues in a clockwise direction as viewed from the top around the disc. If we rotate the hub pictured over the polar chart compass and position the master blade over the 0-degree location, we can then see the balance weight in the example was indeed installed at the 300-degree balance disc location. The preceding demonstration explains how phase angles are used to find balance weight locations with manual manipulation of the rotor system. That version can still be used today, but Cooler Vibe has simplified the process for the operator. You no longer need to place the master blade at the observed phase angle of the vibration to find the balance weight location at the correct position on the balance disc, dictated by the orientation of the accelerometer. These tasks will now be done by the computer. Your only task will be installing the correct weight at the proper degree location on the main rotor balance disc as requested by the ground station computer. The main rotor on Velos turns in a clockwise direction as viewed from the top. The compass in this illustration identifies the balance hole locations in the balance disc every 30 degrees in a clockwise direction, starting from the number 1 or master blade position at 0 or 360 degrees. So the process becomes flying Velos in a stable hover out of ground effect. The analyzer computer will take an average vibration reading and determine the amount of weight and where it is to be positioned on the balance disc. As an example, if the ground station creates a solution of 10 grams to be installed at the 30-degree position, you will carefully measure a 10-gram combination of screw, washers, and nut on a digital gram scale and install it at the 30-degree position of the balance disc. From this example with what you have learned, can you identify on the polar chart where the vibration phase angle was located to create this balance weight solution? If you chose the 150-degree location, you are correct and congratulations. You are now a Velos dynamic balance expert. To balance the main rotor on Velos, you will need a good selection of screws, nuts, and washers to be used as balance weight. They must be the correct size to fit the holes in the balance disc. The top row of washers in the tray is much too big for Velos, so when putting a weight kit together, ensure a good selection of smaller washers made from brass, steel, and stainless steel are available. Only steel screws and steel self-locking nuts should be used. What are acceptable limits of vibration? Listed are the industry standards for vibration level classification. Both tail rotor and main rotor on Velos can be dynamically balanced into the ultra levels of 0.05 or less without difficulty, unless there is a deficiency in the aircraft. These possible deficiencies will be discovered and corrected during the pre-balance inspection before the balancing process begins, but for now, let's consider our aircraft is in perfect working order. Tail rotor balancing is very similar to the main rotor, but with some differences. The analyzer is tuned to 7,000 RPM to sense tail rotor frequency. This may vary on your aircraft because of mission requirements, but it is very important for the proper RPM to be selected. Another difference is the tail rotor has no balance disc for adding balance weight. Adding weight to the tail rotor for dynamic balancing will be done by adding small pieces of clear packing tape wrapped around the leading edge of the blade's span-wise CG location. To perform a dynamic tail rotor balance on Velos, the aircraft must be prepped for the process. First, remove the main rotor blades to prevent the main rotor from influencing tail rotor vibration while the analyzer is sampling vibration data from the tail rotor. The tail blades must be positioned and locked in their blade holders with their centrifugal center of mass passing through the center line of the tail blade retention bolt and center line or centrifugal axis of the tail rotor output shaft. Finding the centrifugal center of mass of the blade can be found in two ways. One method would be to set the blade holder in a perfect vertical position using a vertical laser line. The laser line must be carefully adjusted to create a perfect vertical reference. With the tail blade holder in the vertical position and the laser line bisecting the blade retention bolt and center of the tail rotor output shaft, the tail blade will be mounted into its blade holder with the blade retaining screw. It must be noted at this point that the blade must be free to swing on the blade screw to an unrestricted vertical hanging position. If the blade does swing freely to its centrifugal center of mass, the blade screw nut can be carefully tightened to capture the blade in that position. Accuracy is important in this process, and the blade screw nut will be torqued to prevent any blade movement. The blade must be locked solid in its free hanging position when tightening the nut to capture the blade at its centrifugal center of mass. It is important that only the nut be turned when applying torque. Turning the screw when torquing will move the blade away from its vertical alignment. If the tail blade is too tight in the blade holder to allow free unrestricted swinging to find its centrifugal center of mass, this can be found with another method. The tail blade can be allowed to hang freely on the smooth shank end of a small diameter drill bit. This drill bit will be squarely drilled into a piece of wood. The drill bit will then be inserted into the drilled hole, leaving its smooth shank exposed to allow friction-free vertical hanging of the tail blade. Using the laser set up to project a perfect vertical reference, the laser line will be set to bisect the tail blade screw hole. With the blade hanging freely in the vertical position, the centrifugal center of mass at the tip of the tail blade is identified by the laser line and can be accurately marked at the blade tip with a dot from a permanent marker. Now that you have the tail blade's centrifugal center of mass identified at the tip of the blade, you can now remount the blade back into the blade holder. Remember, this method is for blades that are too tight in the blade holder to swing freely to find their center of mass. With the blade mounted in the blade holder with its untorqued screw and nut, the blade can now be manually swung into alignment, aligning the vertical laser line with the three aligning points, which are the centrifugal axis or center of the tail rotor output shaft, the center of the blade retaining screw, and the dot at the tip of the tail blade identifying its centrifugal center of mass. Torque the blade screw nut using the same precaution as before to prevent misalignment of the blade. With all three tail blades now locked solidly with their centrifugal center of mass aligned with the center line of the blade holder and the centrifugal axis, we will move on in the process. It is important to know that from this point forward, the tail blade's alignment position should not be disturbed. If removal of blades is necessary for any reason, a realignment of the assembly must be done along with a dynamic balance check with the Cooler Vibe analyzer to ensure accurate balance is maintained. With the tail blades locked solidly with their centrifugal center of mass perfectly aligned with their centrifugal axis, we can install the accelerometer and IR optic eye on the tail case. The sensor brackets shown in the photo to my left are the beta version of the brackets. These brackets will be redesigned for the production dynamic balancing system, but their function will be the same. With brackets and sensors installed, reflective tape in line with the IR optic I-beam will be placed on one tail rotor blade. Like the main rotor, this blade will now become the master tail blade and will be used by the optic eye to determine tail rotor RPM and define the phase angle of the vibration, looking at the maximum amplitude of the accelerometer. Next, and for safety, we will carefully route and secure with tape or tie wraps the cable harness of the optic eye and accelerometer down the left side of the tail boom back to the analyzer to clear the spinning tail rotor arc. Contact of a cable harness with a 7,000 RPM tail rotor would be extremely dangerous. All safety precautions should be observed. With the harnesses secure and safe, we need to disconnect the tail rotor rudder rod from the tail servo. Lock the rudder rod against the side of the tail boom at the servo location with foam block and tie wrap, locking the pitch angle of the tail rotor blades to 0 degrees or trail position. This will prevent any pitch change and thrust being produced by the tail blades during the balancing run. Like the main rotor, the analyzer will be programmed to reflect the direction of rotation of the tail rotor which, unlike the main rotor, is in a counterclockwise direction as viewed from the right-hand side of the rotor disc. The location of the IR optic eye identifies the 0-degree location of the master blade, or the blade with the reflective tape. With the master blade over the tail boom, it will be at the 90-degree position. Pointing straight up will be 180 degrees, and pointing straight aft will be 270 degrees. Phase angle locations can now be identified. Remembering the design logic of the accelerometer, where will the light side of the rotor disc be identified with the accelerometer mounted in its position above the tail case pointing straight down? If you said the bottom of the rotor disc or the side where the optic eye is located, you are 100% correct. With main rotor blades removed and the tail rotor blade assembly configured for the balancing run to include securing the rudder rod to create a 0-degree pitch setting on the tail blades, we need to accomplish one more safety measure. A safety lanyard or strap must be looped around the payload rail and fuselage side plates, then secured to anchor the aircraft and prevent aircraft movement should accidental pitch be applied to the tail rotor. This safety strap should not be tight, but should be loose. A tight tie-down of the fuselage during tail rotor balance runs will negatively affect the sensing of tail rotor imbalance. With the aircraft properly prepped and safety measures taken, we will start the aircraft and allow the main and tail rotor to build up to full RPM. The ground station computer will be set to sense tail rotor frequency, or RPM, and will take a vibration average from the accelerometer. With the vibration's phase angle and amplitude now known, the computer will create a solution and provide instruction on which blade or blades and the amount of weight or blade tape that will be added to correct the imbalance. As an example, the computer will request a specific amount of blade tape added to blade number 1 and 3. The clear packing tape will be cut to the specific size or weight required and applied to the blade by wrapping the tape around the leading edge of the blade centered on the blade's span-wise CG. The blade should be cleaned with alcohol before applying the packing tape weight. The service life of the tape is exceptional when blade cleaning and bubble-free application of the tape has been achieved. After the requested tape weight has been applied to the correct blade or blades, another run will be accomplished. On this second run, the analyzer will see how the tail rotor reacted to the balance weight applied, and learning from that reaction will adjust the phase angle and weight required for the second solution. This process will also occur with the main rotor and will continue until ultra-low vibration levels have been achieved. For both main and tail rotors, on average, about 3 runs will be necessary until the target balance has been achieved. Additional information will be supplied with the Cooler Vibe Velos balance kit. Now it's time to talk about the pre-balance inspection of your aircraft. In order to carry out a dynamic balance procedure or any maintenance procedure on Velos or any other aircraft, a preliminary inspection must be done. In this case, the preliminary inspection is carried out to ensure you have all the equipment necessary to complete the task and that the aircraft itself is airworthy and in a condition conducive to the success of the dynamic balancing procedure. In this case, we will ensure Velos is complete with no defects in airframe or worn or loose dynamic components. The accelerometer used on Velos to detect vibration is extremely sensitive, and as I like to say, it sees everything and never lies. If you have any defects in your aircraft, the accelerometer will find them. Basically, when doing a preliminary inspection before dynamically balancing the rotor system, we will be searching for anything loose on the aircraft. One of the first target areas to be inspected and the easiest to correct is the main battery mounting method. Because of their mass, they can quickly double the existing vibration in your aircraft if they are not restrained or strapped down properly. Early versions of this saw Velcro being used. This method of securing batteries is of the hobby mentality, but we are professionals. Velcro should never be used for main battery hold down or in securing anything else on Velos that has any mass or weight. Strapping 4-pound batteries down on Velcro is like strapping them down on top of a mattress. If you want them to bounce around, that's perfect, but we need them to stay perfectly motionless as to not affect vibration on Velos. For securing all main batteries on Velos, cat tongue tape should be used. It is perfect for the job with its ability to grip the plastic battery cover very tightly when the battery strap is tightened up. The cat tongue tape should be applied to the outermost edges of the battery trays to allow the battery to contact as much battery tray area as possible for secure mounting. The rear battery strap should be looped around the fuselage side plate, so when tightened down, the battery is drawn both down onto the battery tray and at the same time up against the fuselage side plate, providing superior battery support for a vibration-free ride. Thin EVA foam should be placed between the battery and fuselage side plate to protect the battery from chafing with the side plate or hardware in that area. For securing the front batteries, cat tongue tape should be applied to the battery trays in a lateral orientation, as shown to allow different size batteries to be used but still have complete lateral contact with the battery tray. This method will prevent rocking of the batteries no matter where they sit on the tray when strapped down. It should be noted that nothing is applied to the batteries when using cat tongue tape, which is also an advantage. Following these guidelines, both front and rear batteries should fly on Velos with minimal vibration. While on the subject of batteries, it should be understood that the normal battery load carried on Velos for the mission normally flown should also be the battery load when doing both tail rotor and main rotor dynamic balancing. Battery mass adds to the mass of the fuselage and will affect vibration mitigation outcomes. You should never change battery sizes in the middle of doing vibration mitigation runs. Keep the weight of Velos constant for quick and accurate dynamic balance solutions. Now that we have ensured the main batteries can be carried on Velos in a secure vibration-free manner, let's take a look at other areas on the aircraft that could negatively impact the vibration mitigation process if not corrected. Remember what I said early in this presentation? Worn or loose parts will prevent Velos from being balanced into the ultra-low vibration levels. If your aircraft is a new build with no accumulated flight time, you are now ready for the dynamic balancing process. But if you have accumulated flight time, we need to look closely at those areas that may need to have worn parts replaced before balancing. Anything loose on the aircraft is your enemy when combating vibration. The entire aircraft structure should be inspected to include landing gear legs. The main canopy actually reduces airframe vibration, so Velos should always be flown with canopy installed both on a mission and during the dynamic balancing process. One area that deserves close inspection will be all flight controls and linkages. Plastic ball links are a prime target. To inspect, grasp the leading and trailing edge of the main blade with your thumb and index finger and gently rock the blade in pitch. If the blade feels firmly held in its pitch position, the ball ends on the control links are good. If you feel free movement in pitch on the blade, the ball ends need replacing before dynamic balancing begins. Ensure the flight controls are properly rigged after ball link replacement, and also ensure both blades 2 and 3 match the master blade's 0-degree pitch setting after rigging. Before closing this presentation, I need to mention 3 more important points when dynamically balancing Velos. Number 1, static balance of the rotors is not necessary before the dynamic balancing process. Dynamic balancing is most accurate, so any static balancing you do will probably be changed during the dynamic balance process. Number 2, never apply clear packing tape to the main rotor blades for balance. The aerodynamics of the blade will be affected, and from that, strange dynamic vibrations will occur. Tail blades are not affected by this, and clear tape works perfectly for dynamic balance in that area. This should also tell you keeping your blades clean is very important. Fly with clean blades, clean off the bugs and dust. And number 3, ground dynamic balancing of the main rotor is not necessary. Only hover balance out of ground effect should be accomplished when dynamically balancing the main rotor. My background covers 44 years as an FAA certified full-scale helicopter mechanic, maintenance instructor, and maintenance manager working for PHI Incorporated. After my retirement, I was confronted by an old friend, Norm Serrano, pictured on the left in the upper photo, who is the driving force of Cooler Vibe and whose chosen profession is perfecting the art of balancing helicopter rotors and has balanced countless rotors for PHI and other helicopter operators for decades that continues to this day. The question was, could we take what we have learned in the full-scale helicopter world and apply it to the smaller scale single-rotor helicopter drone? The short answer is yes, but only after a year of experimenting with countless flights being performed with each flight teaching us what we needed to know. Making new discoveries with these flights required design changes on Velos, and my good friend Eris, the owner and designer of Velos rotors, shown in the bottom photo on the right, listened closely and through his aviation design genius, made the necessary design changes to make the main rotor on Velos to be one of the best, if not the best, in terms of smoothness in flight and most convenient with the removable rotor blade system that will allow the main blades to be removed and reinstalled without affecting the ultra-low vibration levels achieved during the dynamic balance process. It has been my privilege and honor to work on this project with Eris and Norm, and it is my hope that this presentation will advance all Velos aircraft into the elite world of smooth helicopter operations. Your payload will thank you, and I thank you and hope you have enjoyed this presentation.